So, as the world's only professor of algebraic surgery, this is going to be a lecture about algebraic surgery. And algebraic surgery comes from geometric surgery. So, geometric surgery input an n-dimensional manifold M and embedding Sk cross Bn minus k in M. And the output the new n-dimensional M prime, the closure so that of course goes back to the early 1950s. Well, the work of Tom. He invented the word surgery, or chirurgie, and Milner was the first person to kind of systematically investigate this in the late 50s, when he was using surgery constructions to construct families of exotic spheres. But the basic idea is very simple. You have a manifold, and you have a sphere across a disk. There's M naught. M naught is the closure of M minus. And what I'm trying to draw a picture of here is the trace of the surgery. So the idea is that this is the basic operation of changing one manifold to another, in this kind of, which is particularly effective in high dimensions. And the relationship between M and M prime is in particular they're cobordant, and I'm drawing here the cobordism. And the cobordism is called W, always W. And this W is constructed in a very symmetric way, which always confuses people whenever I draw this. Because here I'm going to put in dk plus 1 plus dn minus k. And what's confusing about this picture is, of course, the boundary of this has two bits. And here I seem to have two disjoint, a sphere cross a disk cross a sphere. So one must realize that what's happening in this picture is a collar of both this sphere cross disk and this disk cross sphere. So there are actually three components, but not components, three parts, which unite to form this. So this is not entirely easy to see the first time around. So maybe I'll draw a picture, but another picture. But there are two important things. Every cobordism of manifolds, this is the trace, of course. Let's call M naught, M1. Let's call this P naught. Is a union of traces of surgeries as above. This is Morse theory. So this was the theorem of Milner's, which not only was constructive in the sense of explaining how to construct one manifold from another by surgery, but more importantly, that it's not just every cobordism of manifolds, it's a bit like a theory of compactness. So this is the trace of, so this is called actually a K surgery. same K, of course. So this is going to be K0 surgery, trace of K1 surgery, K2, and so on. Finite number, but quite large, K big N. And the K0 can be, well, it can be negative. You could actually have negative, which is not quite fair. You could have K minus 1. And then the very top dimension that can occur is Sn. Okay, so that's so far I've only talked about geometric surgery, and the algebraic surgery will take this geometric surgery and do the same thing, but not on manifolds, on chain complexes with Poincare duality. So everything that I've said so far on this kind of standard geometric surgery theory works just as well, I claim, in algebra. And what's good about the high dimensions, that in many situations, but not all situations, geometric surgery corresponds to algebraic surgery. Now, it's not quite true. That's, I mean, you have to work in some kind of relative situation. So let's just look at some special cases of geometric surgery and what it does to in algebra. So the examples of low-dimensional surgeries. And then I'll explain what happens in algebra. Supposing M was S1, and then S0 cross D1, S1. So now there are two possibilities. Okay. Surgery, there are two possibilities. What's very important here is these two possibilities are kind of beginning of the whole difficulty of the called charm of the whole business. How the choice of sphere cross disk in N, which has to be captured by algebra, is very delicate. So even so you have 2 points. Let's take our S0. And now you can take S0 cross D1. N prime is either this. So that's after I removed this is the bit which I removed. It was colored chalk. I could use it, but as always, one forgets colored chalk after you need it. So these are the bits which I've removed. And I've put in a tube. So this is about this, well, let's just state like that. Or so that's homeomorphic to 2 circles. This is homeomorphic to a single circle. So it's a very drastic change according to the orientation here, basically. So if I take the 2 D1s to be parallel, I get one of them. If I get an anti-parallel, because at this joint, I get the other one. So it's kind of the most important invariant of a manifold is its connectivity. So you started off with a circle, you ended up with 2 circles or 1 circle. And the trace, that's the most famous cobordism there is a pair of hands. Let's call this case A. Case B, A is a cylinder. I think it's a cylinder. I have to think a little bit. So I'm sure that that's the, so if I go from here to here, what else can it be? Well, it cannot be. Let's pretend that any complaint. If I do this, if I take these anti-things, then you get, so let's just see. This is the W here is M cross I, union D1 cross D1. And this is also the case here. I'm not entirely sure that this is, I'm not entirely sure that this is just a cylinder. Whether it's not actually, this could actually be a Möbius band punctured. So there's a question. So I think it's actually is a Möbius band, because you get a non-orientable manifold. You see. So that's another thing. This manifold is orientable. Sorry, I still got it wrong, haven't I? No, it's fine. The cobordism is non-orientable. The boundary parts are just two circles. So it's a non-trivial cobordism from a circle to itself, as opposed to the non-trivial cobordism from a circle to two circles. So that's something, I hope, apologies. We might have to do some judicious editing afterwards. Okay, so I'll deal with this in algebra. So one of the things that algebra is supposed to be very good at is that you can predict the algorithms. So here you need some kind of geometric intuition to understand when you do this trace business, do you get the Möbius band, cobordism, or the cylinder? I'm pretty sure it's actually the Möbius band. And the reason is that there are two line bundles over a circle. The trivial one and the Möbius band. And that's what's happening here. So perhaps no editing required after all. Okay, so this is another example, of course, is you take another low-dimensional example where it's kind of easier to see what's happening because it's more familiar. This was for when you take M to be S2 and S0 plus D2. And again, you can either have a kind of oriented situation, M prime is a torus, where you kind of do this, or if you take opposite orientations, but now it's the Klein bottle. This again is slightly confusing here.
Have you gone inside?
There's something. Sorry?
And for the Klein bottle, you have to go inside and then.
Yeah.
You don't know?
What I'm kind of proving is the Klein bottle is coordinate to the two-sphere, which is true. There's a projective plane which is not coordinate to the two-sphere. So I'm happy. So it's actually true. So you have to go inside here, exactly. You have to kind of, it's because of the orientations being like that. And so it's the same situation as before with orientations. And then you get some kind of nice cobordisms, the traces of these surgeries. And again, all the kind of geometric invention you need, which I don't have really, I can, I hope, recover from the algebra. Now, so the question, so here I said that the surgery process has this input of an embedding, and one can ask, where do I get these embeddings from? Right? I mean, and for example, there's a general, so where do embeddings come from? Let's have a, well, there's a general theorem called the Whitney embedding theorem. I'll try to not disgrace myself. You don't really need a sphere, you need an atom manifold. So if 2L is less than N, and N is greater or equal to 5, I think that's correct, can approximate every map by an embedding. So there are general theorems by an embedding. And if I had 2L equals n, and I could have an immersion sort of embedding. Okay, so that's one kind of good thing. There are lots of embeddings, at least below the middle dimension. And that would be one of the themes, that below the middle dimension, that you can do things. However, not everything. And the other question I can ask is, why does one want to do so? What does one want to do surgery to do? So what does one want to use surgery for? And the answer is to try to make manifolds as small as possible in the following sense. We have cobordism is equal to surgery. So now you take a manifold and you can ask, is the manifold null cobordant? So that's a kind of good question. And one kind of inductive procedure, pioneered by Kevin Miller, is you try to make the manifold as highly connected as possible. So you make it connected, you make it one connected, two connected, and so on. And at each stage you do as much as surgery as much as possible to make it. So the aim is to make manifolds connected. If you can't, well then you know that the manifold is quite complicated. And then you do something else. So next. What is the purpose of surgery? I should say that the methods of cobordism theory don't actually use surgery theory. Surgery is used for something slightly different. To decide if a manifold. So this is slightly an artificial thing. It's a very good educational question. So if a manifold M can be simplified, e.g. now cobordant, so make step one, make M zero connected. Let's assume it's connected. So for example, if I had two circles and reverse that other surgery, and I can form a tube like this, and I now have a connected manifold. So for adding tubes, making connected sum, I should say, connected sum of components equals zero surgery, effect of zero surgery. So making so supposing, just slow down a bit, supposing M was disconnected with two components, every n manifold has inside it an n disk. And I just want to make sure that one of these two n, the n's is in here and that one is in here. And then in this case, m prime this is exactly the definition of the connected sum. So if m1 and m2 were connected, but this joint in here, they become connected in here. So that's m0 and m1. Okay, so that's easy. Making manifolds connected by surgery, no sweat. But already, the situation with I1 is hard in general. But the next stage, make a zero connected one, Mn, one connected, if possible. And the answer is it's not possible. in general, not possible in general. Let's try to, so this would by one surgeries. Okay, so you would like, so this is kind of, take the manifold. So the standard idea would be, take a non-zero element. If G can be represented by G S1 plus D minus 1, then M prime a nice exercise in the Van Kampen theorem has, for at least for n greater or equal to 4, the first time that you can see explicitly why in high dimensions, has pi 1 of m prime, pi 1 of m, so it's smaller. That's the normal subgroup generated by this. So you can kill, if you can represent an element in the fundamental group by a framed embedding, you're laughing, you can do this, and by doing some kind of calculations, you can work out the effect on the fundamental group of this surgery. And one of the things that algebraic surgery is good for is calculating the algebraic effect, well, not so much for the fundamental group, so that can be done, it's not so, but for the higher homology, higher homotopy groups. And let's see an example where it's not possible in general, where you cannot do this. And this example is just as real, so to speak. It already lives on the chain level, let alone on the kind of manifold level. It's a very simple example. And it's a case where there is an embedding of a circle, but it's not framed. Okay. So let's have a 3, 4. This was 5, I think. For example, MRP2 G, not non-trivial element in the fundamental group, which is of course Z2, can be represented by an embedding by S1, which is RP1 living in RP2. So that's wonderful. But the known bundle, it's called the one-plane bundle, is non-trivial. So the first exercise in constructing Stiefel-Whitney classes in Willner and Stashev, of course, is non-trivial. So by the tubular neighborhood here, so one is stymied. You just cannot kill that fundamental group, which is just as well, for good reasons. There is no, it has to be twisted, it has to be the Möbius band. You can find a Möbius band around the circle, the middle circle, and that's fine, but it's not good enough. You're moving a Kreuzkap, is a technical term, which is perfectly okay, a Kreuzhaube, as it was called in Germany 100 years ago, but it's not surgery. It's not S1 cross D1, it's a Möbius band, and that's not the same thing.
Okay. You always embed an S1 as the generator, as the class you want.
Well, yes. In fact, you can do it for surfaces,
yeah.
And so you can do it for, yeah. So the embedding is not a problem, it's the normal bundle. So that's very important. One reason why surgery theory has a slightly difficult reputation is that you have to know about manifolds, tubular neighborhoods, lots of differential topology, but also lots of vector bundles, and it's all kind of standard stuff. But then you also need all this algebra. So you need everything. And of course you need characteristic classes, you need a lot of quadratic forms here in the algebra. So that it's a kind of melting pot of all kinds of cultures. Now, so already to kill pi 1, there's a problem. And also the same thing arises in pi 2. Soon, even worse, so to speak, for pi 2, e.g., if you take the generator g not equal to 1 in pi 2 of CP2, so I can take, well, 1 because I'm going to record this as z, not 0, so I mean, it's not 0, you can get the non-trivial element, so not 2. And then again, there is CP1 living inside CP2, but the normal bundle is the Hopf bundle, non-trivial, hopeless. No, normal bundle, Hopf bundle, not trivial, not trivial neighborhood. Okay, so that's perfectly okay, but it means that there are difficulties. Okay, so one can try to, before I do any of the sophisticated quadratic stuff, I'll just try to write down what is the effect on the chain level of geometric surgery. And so I'll define chain complexes with symmetric structure. And a manifold, what's good about this theory, which goes back to Mischenko, is that it's extremely easy to see where the geometry comes from. It comes from any manifold. So, that's the definition. The definition will work for any ring with involution, but let me just first not make such a complicated thing. I'll just define it an n-dimensional symmetric complex, but I will call it over Z, is a, and it's quite important, the word concrete doesn't appear yet. I said it, but I'm not part of the definition. It's an n-dimensional, finitely generated free Z module chain complex. Fortunately, that's not enough. So what the chain map, I should say, so let me just draw it. So C upper R always means, it's over Z, just the dual. And then there's D, D star, phi naught, C minus 1. All the way up to Cn. However, this is a perfectly good thing, but it's not enough for the you can just look at this structure, but it's not enough really. The full glory, together with higher chain homotopy, So what do I mean by a higher chain homotopy? So firstly, the first one, not yet higher, is this. So T phi naught is plus minus phi naught star. So the point about this being finitely generated free is that CR is also Hom Z. The double duality, this is where. If I take the dual of this, I get back that. And there's a natural, so this is CR star. Or this can also be called C lower R star. And so I could tell you, I could just have to say the actual sign, but I won't give the higher signs. So, in particular, phi naught is chain homotopy. This is chain homotopy. Chain homotopy. So before I started a little too early using the word higher. It was chain homotopy. Higher. So let's just talk about the first chain homotopy. It's just a chain homotopy from a chain map to its transpose. Then the higher ones. So this chain homotopy is itself higher chain homotopy to its transpose. So one might think that I'm defining some kind of infinite object, but that's not so. The chain complex is finite, and it's finite dimensional, so at some point you run out of dimensions and you stop. Okay, general phi 2, phi 3. I haven't told you what t is. Maybe I should do that. T is just that. It's just the thing which takes a double dual.
Plus signs?
Well, we should have signs. I'm not going to worry about signs. That's good. If you look at my papers and books to get the signs. There are signs all over the place, which cause a lot of pain. So the general one of these things and the general equation, structure equation for these things is that d phi s plus phi s d star plus phi s. And this includes up to sign, firstly. And by convention, phi minus 1 is here. So that's a symmetric structure. Okay, that's the end of the definition of an n-dimensional symmetric complex. So all these things.
So,
And
except for phi naught, these aren't chain maps.
no, exactly not. That's right.
And
It's
this is a map of module.
yeah.
Yeah.
The Z modules. Z module modules. So that's very complicated in some senses. However, there's one good thing about these structures. Every manifold has one. Right? In fact, not just every manifold, every space with a homology class has one. So where do symmetric structures come from? And there's something a bit grandiose. Where do symmetric structures come from? Well, any space X has an Alexander Steenrod Whitney diagonal chain. Diagonal chain approximation. And I'll write it like this: delta S, Sx to Sx. So it's not quite the same as before, in that I didn't use any, well, X, Sx, the singular chain complex. So that's in other words, a very general thing, the singular chain complex. And this approximation consists, I should say that this has a transposition, and what is going on here is that there is a diagonal map which is fantastically Z2 equivariant. Right? So that's Z. Now here you actually have Cx, and it's called Sx rather. So no problems here. The problem comes with the application of the Algebraic theorem. There is a chain equivalent. It's called Ez naught. And that's indeed delta naught is Ez naught delta. But Ez naught is not Z2 equivariant. So there are two actions of Z2. The one coming from the geometric transposition and the one coming from the algebraic transposition. And they only match up to higher chain homotopes. So that's a very sad state of affairs. But that's exactly what's avoided in the ramp homologies. That you can match them up. There are no Stinot squares in the ramp homology. That's okay. But well, so this whole business is made more complicated by the fact that the diagonal chain map, this thing, is only chain homotopic to its transpose, but not actually chain homotopic. So that's and the failure to be chain homotopic to its transpose, well, that's what the higher delta S's are. So let me just write down exactly. And again. And these, in a moment, which I'll define, that's very abstract, but the motivation came from these things. And they're very natural and very hard to define because you need the whole theory of acyclic models. You don't actually get very nice formulae directly. Well, it's relatively hard to get this Ez naught. But you know it exists. Now, they were all in and around Princeton, but at different times. First Alexander, then Steenrod, then Whitney. I don't know if they spoke to each other very much. Get to meet Steenrod and Whitney, 2 out of 3. Now, let's think more what to do now. We're going to try to explain how this structure gives us these things. If X, I should say, I won't tell you now, but this is the reason why this is the kind of underlying chain construction which gives the C0 squares in But the thing about the C0 squares is that they're very important, very useful in surgery theory, but only in a simply connected case. If you have a fundamental group, which is non-trivial, and you want to do surgery on non-simply connected manifolds, then you have to work over the group ring, and all these very wonderful mod 2 invariants are no good, sadly. Okay, so that's one of the many advantages of the chain complex theory, is that it allows one to escape from the original mod 2 calculations or integer calculations to the realm of group rings, which have not such good algebraic properties as rings, but that's what we have to work with on infinite manifolds. Okay, so if X is a CW complex, can replace Sx by cellular chain complex. Of all the singular syntheses which are, well, one for each cell, so to speak, that generates a chain homotopy deformation return. And now, if X is an n-dimensional CW complex, so the kind of homological input here is very general. It just has to be a CW complex and a homology class. No local geometry, no Poincare duality, certainly not a manifold. And X is a homology class. So let's have position is an n-dimensional symmetric complex C phi with phi naught the cap product. So every time you have a homology class, you get a chain map from the cochain complex to the chain complex with the dimension shift. So that's very nice. And now, so that's kind of basic, the lots of them in other words. And so it's relatively hard to actually write down these things for any particular example, because the conception is so general. There is some kind of reassurance that every time you have a space and a homology class, you get one of these. So there are lots of them around. But the difficulty is that you have so much information, it's actually relatively hard to process it. But it is there.
Also, I could choose some non-fundamental class.
Yeah, the theory applies to any homology class.
Okay.
And to any space. In fact, I mean, it's convenient. The reason why you want it to be CW complex is because you want the chain complex to be finitely generated free. And in fact, CX tensor CX is isomorphic by this universal property of the tensor product. There. So I should have included this information. Because these are maps from the co-chain groups to the chain groups, but they correspond exactly to the tensor product which featured over there. The advantage of the tensor product is that you don't need to have any finiteness assumptions. This only really works when CX is finitely generated free. Finitely generated free, as it is for a finite CW complex. So, let's carry on. So now I will use the word Poincare. And then I'll suppose the next position would be if X has Poincare duality, then C phi has Poincare duality.
So this thing you said about Aram cohomology,
Yes.
is that particular? It must just be about the coefficients.
Yes, because they're real coefficients.
Right.
And the point about the wedge product of forms is that it's symmetric or anti-symmetric on the cochain level. So if you take the exterior product of forms, you don't have the problem with cap. On the chain level,
Right.
cochain level, cap product is just not symmetric. There is a, it isn't.
Right, yeah.
Because of the back and front faces, it's kind of a, it comes from looking at the beginning of the simplex and the end of the simplex, and if you switch things around, it's not the same. In fact, a lot the Steno's work especially use simplicial complexes and not singular. It's only with Algebraic, with 100th anniversary, this is born 100 years ago this year. So it was, I think I would like to say something about Heidelberg, which is that when Steenrod, I met Steenrod, he was in Cambridge in 1970, giving, he spent a whole year there, and he died shortly thereafter, as soon as he went back to Princeton. So he gave a whole course, but that was very interesting about cohomology. But also he gave us a topology seminar. And the topology seminar was billed as a personal view of the history of algebraic topology. So of course I was just beginning graduate student, thought, the great man will tell us about the great things he did. But he was very modest, and he talked about 3 advances in topology, which he completely failed to appreciate at the time. And the first one was singular homology. He actually wrote on the blackboard that when Eilenberg came to him with singular homology, he actually wrote this on the blackboard: cheap, flashy, glittery.
Cheap.
Flashy, glittery. He didn't quite use the word foreign. He was far too much of a gentleman, but that was somehow always for that. So that was the second thing which he failed to appreciate. He said, it's true, spectral sequences. So in the 50s, when Serre's thesis brought in these fantastic homological methods, which were so powerful, Steenrod thought this was all wrong, and it wasn't very geometric, and this and other. So for 10 years afterwards, his graduate students had to write out all their proofs using exact sequences. And then in the early 60s, disaster struck. He needed a spectral sequence. And there's something called the Rothenberg-Steenrod spectral sequence for homology of classifying spaces, which is a good spectral sequence, but it is a spectral sequence. So he had to eat his pride, and just, there are good things for computational purposes. And the third thing, which he said he had failed to understand or appreciate, were the semi-simplicial methods introduced by Kahn, which are kind of absolutely essential these days to modern algebraic topology. And somebody, one of my older colleagues, said he was right there, but he was wrong. Okay, so that's my story about Steenrod. Next, 11. So let's have another definition. An n-dimensional symmetric complex C phi is Poincare if phi naught is a chain equivalence. So Poincare duality. So proposition of if X is a space with CW complex, with a fundamental class such that let's have it n-dimensional one, just for safety, otherwise freeness problem, but not functional problem. So it X is an n-dimensional CW complex with a homology class just like before, such that this cap product i.e. Poincare duality then this thing here, which we'll call phi x, then Cx phi x is an n-dimensional symmetric Poincare complex. In fact, it's an if and only if statement. If and only if. If this is Poincare, this is an isomorphism. So that's not surprising. I mean, it's all kind of the definition of a symmetric Poincare complex or symmetric complex was tailored for this theorem. I mean, if there weren't examples coming from geometry, it wouldn't be such an interesting theory. But if, I'm not going to ask ask, of course, whether every symmetric complex comes from, obviously the answer is no, because, for example, for a space, for a general to a space, the zeroth homology is always Z, or if it's a non-empty space, so it's a free abelian group at least. And here you could perfectly well have that C0 is 0 in abstract, but still, subsidiary questions. Okay. So what does this have to do with surgery theory, all these surgeries? Well, turns out two things. There's a generalization of all this, not just to Poincare complexes, but algebraic analogues of cobordism of Poincare complexes. And I won't get to it, I'm afraid, today, but next time I'll talk about the theorem which says that every cobordism of algebraic Poincare complexes is a union of algebraic surgery, traces of algebraic surgeries. So I think I'll stop now. This is as much as anybody can be expected to take, maybe even give. And so I'm afraid I'm taking over next week's lecture also. Okay.